File systems use several techniques to try to minimize the accesses to disk and to improve the file access overheads. Much like hardware caches are used to temporarily hold recently used data and avoid accessing main memory, file systems rely on buffer caches, except these buffer caches are present in main memory, and they're used in order to reduce the number of necessary disk accesses. With caching, the file will be read or written to from the cache, and periodically any changes to the file that have not been backed up on permanent storage will be flushed from memory to disk. By forcing these flushes to happen only periodically, we can amortize the cost of performing a disk access over multiple intermittent writes that will hit the cache. File systems support this operation using the fsync system call. Another component that helps reduce the file access overheads is what we call I/O scheduling. This is the component that orders how disk access operations will be scheduled. The intent is to reduce the disk head movement, that's a slow operation, and we can do that by maximizing the number of sequential accesses which are needed. So for sequential accesses, the disk head movement is not expensive. It's expensive for these random accesses, so that's what we want to avoid. What that means is, let's say we have two operations that have been issued, write block 25 followed by write block 17. And if the disk head is at position, let's say 15, these operations will be reordered by the I/O scheduler so that they're issued as write first block 17 and then block 25. And this will achieve this objective of maximizing sequential and minimizing random accesses. Another useful technique is prefetching. Since for many workloads there is a lot of locality in how the file is accessed, it is likely that if one data block is accessed, the subsequent blocks will be accessed as well. File systems can take advantage of this feature by prefetching more than one block of a file whenever a single block is accessed. This does use up more disk bandwidth to move larger, in this case 3x worth of data from disk into main memory, but it can significantly impact or reduce the access latency by increasing the cache hit rate, because more of the accesses will be served out of cache, potentially. Finally, another useful technique is journaling. I/O scheduling reduces the random access, but it still keeps the data in memory. So these blocks 17 and 25 are still in memory waiting for the I/O scheduler to interleave them in the right way. That means that if something happens and the system crashes, these data blocks will be lost. So we want to make sure that the data ends up on disk, but we still want to make sure that we reduce the level of random access that's required. This is where journaling helps. As opposed to writing out the data in the proper disk location, which will require a lot of random access, we write updates in a log. So the log will contain some description of the write that's supposed to take place. If we specify the block, the offset, and the value, that essentially describes an individual write. Now, I'm over-trivializing this. There is a little bit more that goes into it, but this is overall the nature of the journaling or the logging-based systems. The follow-on file systems to ext2, called ext3 and ext4, that are also part of current Linux versions, they use journaling, as well as many other file systems. Note that a journal has to be periodically updated into a proper disk location, otherwise it will just grow indefinitely and it will be really hard to find anything. So if we look at these four techniques in summary, every single one of them contributes to reducing the file system overheads and latencies. This is done by increasing the likelihood of accessing data from memory, by not having to wait on slow disk head movements, by reducing the overall number of accesses to disk, and definitely the number of random accesses to disk. These techniques are commonly used in current file system solutions.